There we go. Now we're recording. Okay. So can you all hear me? Zoomers, people, roomers, as it were. Can you all see the formative assessment?
Yes, we can.
Awesome. Technology working today. So thank you for your efforts and answering these questions and also posing some questions for me. We'll talk about this as a means of review. So in what situations, first question here, would you expect the unique effect of a predictor slope to differ from its bivariate effect? What do you think? When they're inversely related?
Yeah.
That is a more specific answer than I was looking for, but it is true. So if two predictors are negatively related, then oftentimes their unique effects can be larger than their bivariate effects. It's a term called suppression. But more generally, what has to be true for a bivariate effect to differ from a unique effect?
When I need to control for the other predictors.
Yeah, we have to have other predictors in the model. And what has to be true about the predictors then? Yeah, they have to be related. So if you put multiple predictors into the same model, but the predictors were uncorrelated, then you would expect their bivariate effects to look like their unique effects, because what each brings uniquely is everything, because it's unrelated to the others. So there's no competition amongst the predictors to explain variance. So that would be like if each Pearson decided which rooms to clean ahead of time, and then they went and each did their own individual rooms, and nobody cleaned the same rooms, and there was no overlap. So that would be the most efficient course of action. And indeed, that's the logic by which experimental designs are often constructed. If you're interested in looking at more than one feature at the same time, is to assign people to conditions in such a way that your predictor variables are uncorrelated. That way they can each have as much of the variance as possible. Otherwise, it is often the case, but not usually, that the unique effects are smaller than the bivariate effects. The exception is if predictors are negatively correlated. Then it can go the other way. So any questions on that or comments? Feel good with that one?
I don't understand what is good there. They're supposed to be uncorrelated.
I would say that if you can control the situation, then yes, that is optimal. But in an observational study where you're not manipulating things, you're not assigning people to groups, and you can't control the predictors, then you can expect them to be related to some extent. And it's just making sure that you're aware of how related they are and consider that in thinking about what are the implications of your results. So that's why in the example that we just were working on, example 4b, I started by looking at all of the bivariate relationships between each potential predictor and my outcome, because I want to know what's related to the outcome, period. Then when I put them into the same analysis, if a predictor is not significant, I will know whether it was never significant in the first place or it's not significant anymore because of its collinearity or competition with the other predictors. So those are two different conclusions, two different potential reasons beyond a predictor not contributing to the model. Is it competition or is it just not related? And to me, those are different things. Other questions on that? Good? All right. Oh, effect size. What is the difference between semi-partial and partial? I was amused to see how many of you wrote, Lisa doesn't like partial effect sizes. That's not entirely true. I don't like squared partial effect sizes. Now that may sound like a semantic distinction, but to me it's not, and it relates to why they're different and how it is potentially confusing to report partial eta squared. So what's the difference? Let's start with that. What's the difference between partial and semi-partial? They both are supposed to indicate the size of a unique contribution of a predictor. They differ in what it's relative to. So for semi-partial, what's the denominator?
I would say that semi-partial is kind of direct because it says the contributions of one predictor out of the whole model,
Yes.
while the partial effect size shows the contribution of one predictor out of the other predictors, not the model.
I will agree with that. But I will also clarify. So the answer was that semi-partial is more direct because it shows a predictor's contribution out of everything. And so out of everything, I will say sums of squares total is the denominator. It's the idea of like what is the total variability that there is in this outcome, and how much of it is this predictor responsible for. So I like semi-partial eta square. By the way, what's the difference between semi-partial eta square and semi-partial R square? Or semi-partial correlation squared? There's like 3 different ways to say it. Is there any difference? No, there's not. Those are synonyms. So eta means R, basically. So you can talk about semi-partial correlation, semi-partial eta. You can say semi-partial correlation squared, semi-partial eta squared, semi-partial R squared. The difference is whether you're in R or R squared, but eta is a synonym for R. So the difference depends on what package you're using. In SAS, they're labeled as eta squares. In Stata, they're labeled as correlations. In R, it depends on, of course, who wrote the package and what they felt like that day. So squared versus unsquared is really the primary distinction here. And if you talk about semi-partial squared, that is the amount of the model R square that is attributable to that predictor. So how much of the total prediction is because of this? And I like that. I think that's a very useful direct number. The only catch is that you can't always do that per slope. So slopes that share a common reference group, for instance, if you've done dummy coding, you can't get the semi-partial eta square for each one because they don't sum to the right total because they have a redundancy. You have to lump them together. Likewise, if you have an effect that is conditional, that's coming in the next unit, more of those, like an interaction term or a linear and quadratic. The conditional one would change if it were centered elsewhere. So semi-partial eta square is harder to get, but potentially more useful. It's just that sometimes it requires you to lump things together. So we'll see a few more specific instances of that as we go through the example. So that's the one that I like. So then what's partial differs in what it is relative to. It's not over total. It's over the amount of the sums of squares that's attributable to that predictor plus error. So partial is like, how much of what's left did you get? So in the Pearson's example, cleaning the house, like Kevin's partial eta square would be, what proportion of the house did Kevin clean that Randall didn't?
That's partial.
That's partial. So that'd be like, in the book they have a nice example, like if you have a pie, right? I don't bake, but occasionally I will purchase a pie from a grocery store as God intended. And if I sat down and ate half the pie, then it's like, that's gone. And someone else comes up behind me and they're like, how much do you want? Well, I want half. Well, you can't have half because I already ate half. Well, can I have half of what's left? Yes, that's a quarter.
But the number will be quarter, or will the number
Yeah, so then like in that case, if I eat half the pie and somebody comes behind me and eats half of the half that's left, then their semi-partial is the quarter they actually ate, but their partial is half because they ate the half of what's left. And that is confusing. The of what's left is a moving target. So for those of you who wrote, Lisa doesn't like partial eta or partial correlations, I don't like partial correlations squared because the tendency is to think that that somehow has to do with the model R-square, and it doesn't. It's how much of the variance that the other predictors didn't get did this one get? How much of what's left? And that's a moving target. And this is the version that you can artificially increase by adding additional predictors to the model that explain variance. So it makes it difficult to compare those across studies. Question? Mm-hmm.
It gets very confusing to remember which is what in how we are.
Confusing to remember what? I'm sorry?
Like I understood the concept, what is semi-partial and partial, but I forget which one is semi, which one is partial.
I know, these are terrible names. Semi-partial has got to be like the worst name because it's like two wishy-washy words stuck together that's supposed to mean something. And to make it even worse, it is also called part. Semi-partial and part are the same thing. So you may hear that word used in different textbooks or by different authors instead. So here's my strategy. I'm trying to take, and to be honest, I hadn't thought a lot about this until I started teaching this unit and I decided to be more strategic. I think that semi-partial eta squares makes sense to talk about how much of the R-square is due to this thing versus that thing. Like who's doing the work here of the prediction? That's a good way I think of to talk about the relative importance of a predictor or set of predictors. That requires lumping slopes together that describe conceptually one predictor variable. I also think that the ease of taking a t-test statistic and turning it into an effect size, which is partial, is useful because then you're not talking about how that predictor compares like to the R-square, it's just what's the unique effect size. How did this predictor do relative to what's left? So the D's and R's that you can compute out of your t-test statistic, I think those are also useful, but they convey a different thing. So I would do both. You can potentially talk about semi-partial eta squares for conceptual predictors, and you can talk about individual slopes and give them each an effect size as well. In your results sections for manuscripts and things, the only two columns that you really truly need is estimate and standard error, because everything else can come from that. If you take your estimate and divide the standard error, estimate over standard error, that's t. You can then use t to make your effect sizes, you can figure out your p-values, you can make your confidence intervals, you got all of that. So estimate standard error. It's nice for your reader if you do the math for them, but at a minimum, you just need estimate and standard error. So the reason that partial eta squares then, or partial correlations, can look better is if you reduce the what's left part, then their share is proportionately higher. Okay, how are we doing with that one? That's a tricky one. Does that help a little bit? Remember, I decided on the poop emoji for thumbs down. I don't have a sideways one yet. Would anyone like to make a suggestion? What the options are? We can figure out sideways emoji. And that way people who have their cameras off can still participate if they want to. Any ideas? We're all looking now. Except me, because my menu updated myself and I don't know where those are anymore. No ideas? No recommendations? There's just, yeah, thumb sideways. Oh, the surprise face? I like that one. Okay, we'll go with that. So you can have standard thumbs up, surprised face is thumb sideways, and poop emoji is thumbs down. Or emoji poop, as it is called at our house. Because he was 2 when we first saw our very first poop emoji. Okay, Now with that rating system in mind, how are we doing? Couple thumbs. A whole lot of people don't want to play. Thank you. Now they're humoring me. Thank you. I will take a pity thumb. I will. I'm fine with that. All right. Question 3 then. So difference in concept and procedure with respect to testing significance of the model R-square as opposed to change in R-square. So how do I know if my model R-square is significant, and what does that mean if it is? Let's start there. How do I know if my model R-square is significantly greater than 0? Look at the p-value, but which one? Of the model. So what is the test statistic that's associated with that? Where does that p-value come from? What letter? F, yep. Yep, that's the one where if you only have one slope, F is t squared for that slope. So the F test for the model tells us how much prediction per slope it took relative to how much was outstanding per slope we could have added. So it's like, did we get a good deal? And in general linear modeling packages, that F shows up by default. You do not have to do anything special. It just shows up. That is, I think, universally the case. I have never come across a package that did not give that to you in a general linear models package. So if it's significant, then what it means is that R-square is saying that there is a significant prediction of your outcome. There is a significant correlation between the y hat your model created and the actual y. It's saying that the reduction in residual variance is significant because that's what R-square is. It's the proportion reduction in residual variance relative to the empty model. So relative to the empty model with no slopes is the baseline. That's why it's against an R-square of 0. And that you are all very well practiced at this point. So good so far? That? Now the new part, which you get to practice on your next homework, the idea of testing a change in an R-square. So rather than starting with a baseline of an empty model, we might start with the baseline of a model that already has some slopes in it. So then the question is, did adding more slopes help or not help? So it's an incremental contribution to the prediction is what's of interest here. Not relative to the empty model R-square of 0, but relative to what it was before. Did we make it better or not? Now, if I only add one slope, do I have to do anything special to figure out if the change in the R-square that slope created is significant? For one slope. We got one vote of no. It's a yes-no question, 50-50. If I only add one slope, do I have to do anything special to say whether the addition of that slope improved my R-square? Yeah, I'm not trying to trick you, I swear. No, you don't. Because if I add one new slope, and that slope has a significant p-value, then the contribution of that slope is significant. That means the R-square had to have increased. It's a one-to-one correspondence between the idea of the change in the model and the change in the slope. So that's why, when we first started linear models and we had one predictor at a time, I told you to ignore the model part of the output. Because if the t-test statistic for that one slope is significant, the model's significant. It means the same thing. The same is true now. The change to the model R-square, if it's the result of only one slope, if that slope is significant, the change in R-square is significant. One-to-one correspondence. But what if I want you to add 2 slopes or 3? then do we have to do something different to talk about whether the change in the R-square is significant? We do. That's the one new thing in this homework. Because what we need is another F-test. We got to ask for it. F evaluates the contribution to the model R-square per slope, so anytime there's more than one, we got to ask for it. So that is the new contrast statement in SAS, test statement in Stata, and a version of GLHT where you list the new slopes in R. That's the new thing. So in your homework, go over to here, homework 5 is available. So I let you know, I think on Friday. It's due Wednesday, so we'll have 2 more classes before it's due. And I'm calling this homework Amnesty. This homework is very long, but it requires very little code. No estimate statements, no lincomps to do this whole thing. No partial correlations or partial Ds. So the coding for this is relatively easy. Instead, what I'm focusing on is just really drilling the interpretation of what the numbers mean. So it's redundant on purpose, because if you know what a p-value is or you know what a standard error is, you should be able to answer that question 6 times with no problem. It's worth 17 points. That way, if maybe the first time I asked you what a standard error was, you got it wrong, you can earn yourself back. So this is the Amnesty homework. I ran cross country and track in high school. And I would liken this to be like maybe if you're running the mile, which is 4 laps around the track, this is the 3rd lap. Like this is the one where you can kind of back off the gas a little bit to prepare for your last lap where you really have to kick it in to be able to finish strong. So we're backing off the gas just a little bit. The one new thing that this homework is asking for is this idea of testing a change in R-square. That's it. Everything else you've seen. So to keep the workload comparable across people who are using each package, rather than having you write additional code to compute semi-partial eta squares for sets of predictors, I'm asking you just to literally calculate the difference in R-square across models. So you don't have to ask for that. That is a manual calculation. So for instance, on section 2, enter the proportion of variance explained by the model. It wants an R-square. Here's some of my previous choices, clearly. And then in section 3, enter the proportion of variance accounted by the model. And then the next one, enter the change in the proportion of variance. So the difference between what you had in section 2 and section 3, that's the change. By how much did the R-square increase after you added these new predictors? So the part that you have to do in code is this new command to create a custom F-test for the new slopes. And that's what we'll do in the example. Illustrate that again. So that's the one new thing. And yes, it is long, but I promise you, if you know what you're doing, it doesn't take long. And if you don't know what you're doing, then the extra time hopefully will get you to where you know what you're doing, which is eventually the goal. So while I have this up, does anyone have homework questions so far? Yeah?
I have a question in section 72 in the Dropbox.
Question 72. Yes, not a typo. Told you it's a long one. Here we are. Nope. Section 1 then.
Yeah, like it's about the...
Yes, this box right here.
Yeah. I'm not sure whether those options have differences, especially would you like to explain about type 2 error in that case?
A type 2 error is the probability that you miss an effect that's true.
So if the p-value is 0, that means that there is no possibility to miss that implication, probability.
I would say that what a p-value refers to is type 1 error rate.
Yeah.
And type 1 error rate is assuming that there is no effect for real What is the probability that you have a false positive? Type 2 is concerning a different alternative reality, where there is an effect for real, but you miss it. And what we're doing here is testing slopes against a null hypothesis of zero effect. So we are in the former worldview. So I think you can eliminate that choice. That's what I'm trying to say. The others I'm kind of proud of, because they are all very common misconceptions and p-values. So yeah, I'm sort of proud of my nerdiness when it comes to these things. By the way, Jonathan and I won an internal grant from the College of Ed to actually make this a product. So the homework system could be something that other stats instructors at our university or otherwise can eventually start to make their own homeworks. So it could be a thing. Right now, it is a very, very long and kludgy SAS program that underlies all of this, and it is very laborious and error-prone because I am not a programmer. So I did it the best way that I could, which was not a good way. So stay tuned for those developments. But anywho, the story behind this week's homework is we're predicting graduate school performance from GRE scores and fear of statistics, as well as from motivation. Spoiler alert, severe fear of statistics is bad for you. That's the story behind this one. But no one's afraid anymore, right? It's cool now. Or maybe just a little afraid. Like thumb sideways afraid, but not like, oh my God, this class is going to be so horrible. Anywho, other questions on homework? Okay. Then, yeah, that's the end. I thought that was the last one. So then this is the new part, the idea of testing a change to the model R-square. That's what I want to show you how to do. Yeah, one of the nicest compliments I ever got from a student who was interested in taking one of my classes said, I heard from other students that you make statistics actually palatable. It's like, wow, palatable? That is so nice. You had me at, meh. I do what I can. All right. I don't know if I need the slide. I think we're good with that. But I do need this. We were looking at this last time. This is example 4B. Shall we dive back into this? Make it a little more concrete, how to actually ask for these custom Ftests and things. So this is not predicting income, as I promised. This is the data set that will see us out through the end of the semester. These are fake data I made up about a fictional study of older adults based on a real study. 550 older adults were predicting an outcome that is called cognition from age, grip strength as a proxy for physical function, dementia diagnosis, which is a 3-category grouping variable, and gender, coded such that men are the reference group. So last time we went through the setup of all of the variables. So this is something that you've already figured out how to do. And we went through descriptive statistics, so trying to figure out what the ranges are of our quantitative variables to make sure that they're plausible, and also to inform our centering strategy. So for instance, given that the mean of age was near 85 years old, I picked 85 as my centering. Given that the mean of grip strength was 9, I picked 9 pounds per square inch as my centering for that as well. I know that in this data set, at least, gender is a binary variable, and I know that there's 58% women. I coded it so that the men were the 0 and the women were the 1. You can choose either one, you just need to know which it is. And in this case, I am using indicator dummy coding to do dementia group such that none is the reference, and then we'll get each contrast relative to that. In your homework, by the way, though, I asked you to do sequential dummy coding. That's the version that you did for the last homework too. So it's adjacent differences rather than differences relative to a reference group. That will make more sense given that the predictor for fear of statistics is ordinal. So any questions or things you want to review on just getting data in, making variables, running descriptive statistics, stuff like that? No? We're good with that? Reasonably well? Okay. Then last time I believe we walked our way through some bivariate results with respect to Pearson correlations. So we can get a correlation matrix of any set of variables that are quantitative or binary, and that will tell us our bivariate associations among those variables. While this is super convenient because you can get a bunch of relationships at the same time, this isn't necessarily going to tell you everything you might want to know. For instance, I have a negative correlation between age and cognition, such that older people do worse. But this type of relationship that it's describing right here is of a particular functional form, which is linear. So it could be that age has a curvilinear or other kind of nonlinear relationship that we wouldn't know about from this table. Likewise, we can't put dementia group into the table because it's a 3-category variable, and each of the binary dummy codes only means what it's supposed to mean when they're in conjunction with each other and not separately. So I think we did this. We did the empty model. Does that sound familiar? Maybe? Okay. One additional thing from the empty model that I want to point out to you is that in R, I'm using it to save an object, which is the total sums of squares. That's going to show up later in my semi-partial eta square calculations, that value. So I extracted that from the empty model and saved it as an object. So that number is right here. That's my total sums of squares, taking into account the intercept. So that's all the information there is in this variable. If I divide by sample size minus 1 for the intercept, that gives me my residual variance right there. So that's all the variance that there is to be had in cognition. We can see then how much of it is accounted for by each of our sets of predictors. So then we looked at linear and quadratic age last time to see if there was any curvilinear relationship there. Note that both predictors go in the models. If you want to fit a quadratic effect, it only means quadratic if it's above and beyond the linear, so they both go in there. And while we do have a significant model, my F for the model is telling me that the two slopes do work together to significantly predict cognition. How well they work together is like 3% well, which is not great, but it is what it is. It looks like the individual contribution of the quadratic slope for age is not significant, meaning we probably don't need it. And if this single slope that we added relative to a linear effective age is given by Pearson correlation is not significant, the change in R-square it created is not significant either. So this is an example of a one-to-one correspondence. If the thing you added isn't significant, you did not improve the R-square. Did the same thing for grip strength with nearly the same result. Grip strength is a little bit stronger of a predictor, it looks like. We got about 6% of the variance instead of 3%, but the same story, its quadratic slope is not significant, indicating we probably don't need it. Ding dong. There we go. And then we got to here, and I think that was where we called it a day. Does that sound right? I think so. Okay. So then the next bivariate analysis that I'm doing. So I'm calling this bivariate even though the model that I'm fitting has two slopes. Because conceptually, what this represents is one predictor for dementia group. So I'm fitting a model to describe how dementia group all by itself predicts cognition. That way, once I eventually control for age and grip strength, then I will know how that relationship changes. I need to know what it is in the first place. And people are clapping out there. There's a party happening in Lindquist today. No, that's okay. I'm kind of amused by it. It's like having a laugh track that's running to your show that's like off. Like, I didn't say anything that merited applause, but they're high school students and they're getting free pizza and chips, and they're not in school, so it's all good for them. So anywho, model with two dummy-coded predictors that are going to tell me how each of the 1 groups differs from the 0 groups. Cough, cough, homework question. Always, that's what it means. And what would I call this analysis if I were talking about it with people who are not familiar with the term general linear model? What do I call it if I have a categorical predictor of a quantitative outcome? Anova, that's what this is. This is analysis of variance right here. So I'm reminding you then, you've seen all of this before, but just in case, how the model tells us what the mean is for each group. The predicted outcome for each group in this context is usually called a predicted mean or a condition mean, as well as all the mean differences. So here's my equation with the e on the end, gets me to the original y. Then I have my y hat for the none group is composed of the fixed intercept plus then potentially the effect of each slope. However, for the none group, those two predictors are coded 0. So that means that the mean for the outcome for the none group is just given by the fixed intercept. For the other two groups, if I want to know what their means are, these are linear combinations. So I add the slope for the predictor that controls 1 for that group. So beta 0 is the mean for none. Beta 1 tells me how future differs from none. I add them together to get to what it is for future. Likewise, I add beta 0 and beta 2 to get to what it is for current. So given these ingredients as to how the model tells me what the conditional mean is supposed to be for each of these groups here, then I can use that information to work backwards and figure out what the differences are. So none versus future. Future goes here. This is how the model says the mean for future is created. I subtract from it the model for none as my reference, and that means that beta 1 only is how I get the difference of how future differs from none. Likewise, beta 2 directly tells me how current differs from none. So the only one I really need to ask for is this linear combination, how current minus future drops to beta 2 minus beta 1. So then in the code, that's where this combination of -1 and 1 shows up. Generally speaking, anytime you want a predicted difference between non-reference groups, then the group that you want as the reference for that comparison gets the -1, and the group you want as the alternative gets the 1. So you can also see those ingredients work if you look at the lines of the estimate statements up above. If I want to know future versus current, I start with the line for current right here and literally subtract the line that's right above it. So 1 minus this one drops. 0 minus 1 gives me the -1 right here. 1 minus 0 gives me the 1 right here. And then in this case, I'm also demonstrating how to get partial D and R effect sizes out of this estimates table. And so then I added the code to do that, which you've seen before. In Stata, same thing, although I am embedding the effect size code within it. So I've got my first 3 lincoms to get the cognition mean for each group. Here are my 2 slopes inside the model. And then the mean differences immediately after, I embed the statements that give me the R's and D's for that mean difference. So these lines you can copy without changing anything. You can just stick them in there and they'll always work because they're referring to saved output that's internal to the program. If you're using my SAS code, though, you'll have to change degrees of freedom here. And yes, there is a way to make it do it automatically, but it's not worth the extra work that it takes to do it. And our users, we've got the same stuff that we're used to seeing. So here's my model, cognition, squiggle 1 for the intercept plus my 2 slopes. And then I have my GLHT to get the predicted outcomes. So the combinations of 0s and 1s are exactly what they are in the other programs. And you just have to know the order in which you listed these corresponds to the order of the multipliers in these statements. And then saving the results of that, here's our code to compute effect sizes for the GLHT output and then stick them onto that table. So all of that you've seen versions before, but it's good to review ever so often. Okay. Questions on any of that code for a categorical predictor? All right, then survey says, is my model significant? Sure is. My F is 58. My two slopes work together. How well do they work together? Like 18% well. So the strongest predictor. Turns out dementia is bad for you. There's today's update from Cognitive Aging. Solution then, my intercept, expected outcome when my predictors are 0. In this context, that's for the none group. Their expected score is a 27. The expected score for the future group, the people who are not diagnosed yet but are on their way there, kind of like foreshadowing. The future group, as the one group for this comparison, is about 5 points lower. Likewise, the current group is 16 points lower. So the slopes always tell you how the one group differs from the 0 group. So the one group is the one that gets the minus sign, making them lower. And here are my linear combinations. They give me all the means, all the mean differences in one table, and then I concatenated the last 2 columns here of effect sizes to go with them. So now we've got a handle on what are the bivariate associations for each of these variables. We can stick them all together and see what happens. So this final model with all the predictors, you will get to in your homework sequentially. So this homework is different than your others in that I'm asking you to build the model across sections. So you leave in what's in there for section 1 and add to it in section 2. You leave it in and add to it in section 3. And I'm doing that because it's the least amount of work in terms of coding to get the contribution to the Rsquare for each new section. But because I think this is a better strategy to put it all together, because then order doesn't matter. That's what I'm teaching you. So conceptually, we have 4 predictors here. I have a linear slope for age because it looked like that's all we needed, a linear slope for grip strength, a linear slope for binary gender because that's all that's possible for a 0-1 variable, and then 2 slopes that make up dem group. So in terms of things to potentially be lumped together for effect sizes or significance decisions, I need to ask it something for beta 4 and beta 5. Because there's 3 possible differences, this is only 2 of them. But I've got a couple other examples of ways that you can lump things together that would address different types of hypotheses. So this is the new piece. Contrast statement in SAS, test statement in Stata, and GLHT in R that has words in it instead of numbers. So it's a different version of the same command. You can specify these commands in multiple ways. This is easier to do for this purpose. So I'm asking for 3 custom Ftests, 1 for demonstration purposes for the model, and then 2 others to illustrate what it would look like as a real research type question. So this is the one that you don't need to do. Attention shoppers, do not spend the time typing this one. It's already given to you. This is a demonstration. I wanted to show you if, for some reason, you didn't get the F for the model, how you could get it. You list all the slopes in your model, separated by commas with a 1 after each. For the others, this illustrates how to get the contribution to the model R-square, a significance test for that for multiple slopes at the same time. So the first one here is lumping together the 2 dementia slopes. So that's going to give me what in Anova literature we would call the omnibus F-test for dementia group, meaning are there any differences across the 3 means? That's a 2 degree of freedom test. Let's say that I had a hypothesis that I wanted to test the utility of demographic variables versus these other variables. and I wanted to know if the demographic variables added anything. Well, I can answer that. I can lump together age and gender and talk about their contribution as a set. So this is directly analogous to what is called hierarchical regression, where you enter predictors in sets that correspond to some kind of organization scheme, like control variables, and then predictor variables, and then some other kind of predictor variable. You can do it all in one model. So in your homework, when you get to a section that adds 2 or more slopes at the same time, and you want to know if the change in the R-square that you just created by adding those 2 or more new slopes is significant, you write them here. Okay, does that make sense as a concept? We're building custom Ftests for groups of slopes. That's what we're doing. That answer specific questions such as, is there a significant effect of dementia group as characterized by these 2 slopes, or is there a significant effect of demographic information above and beyond other information, functional information, I should say. Go ahead.
So first we do age and sex, and then we do, like we keep adding one by one to, is that what we're expected to do is, first we just see one variable, then we're seeing one more variable, then
yes.
So we're seeing 1 and 2 together in the second.
Correct.
So I was just curious, what's the purpose of doing that instead of just doing one separately and then?
Because if I asked you to do what I'm doing in this handout, people who are using Stata and R have to write like 3 times as much code. And so to try and keep it fair, I'm doing it in a sequential fashion so that you can tell what the change in the R-square is just from subtracting. And you don't have to write a whole bunch of code to get the semi-partial eta square that goes with those new slopes. That's my sole purpose, is fairity. Is that a word? Fairness. What other word am I trying to put together to say fairity? Pretty sure that's not a word. It might be now, though. Equity. Fairness and equity is fairity. That's where I was going with that. I do statistics, not English. Clearly. All right. So yes, in your homework, you are adding things in layers to make it easy to see what the change in the R-square is. In life, adding things in layers makes it easy for someone to argue that you got the ordering of your layers wrong, because the contribution of a variable earlier in the sequence would be higher because it has less competition than a variable that happens later. So the change in the R-square that results earlier is going to be higher than the change in the R-square that results after everything is included, but the latter is a more fairity comparison. Yes, equity or equality. That's where I was going with that, I think. So point being, this is how you ask if a set of slopes contributes significantly to the model and you get an F-test. So here are a couple distinct examples of that. I'm also outputting 2 sets of tables. The one that goes with the slopes, that is called parameter estimates, and the one that goes with this little estimate right here. So this is the remaining dementia group difference that I want, the third comparison that's missing between the 2 non-reference groups. That's being saved into a table. Then I'm stacking those 2 tables on top of each other to generate effect sizes and have them all print in one table. So a little bit more nicer display, I should say, less work. Okay, so any questions on the SAS code? So contrast in SAS gives not only the F-test that we're looking for, but also the effect size for it. That's one thing that's really nice about it. In Stata, then, the analogous new commands to get the custom F-test for groups of slopes are right here. You list each slope that you want tested equal to 0 and put it in parentheses to denote numerator degrees of freedom. So there are 5 sets of parentheses here. That's how I know I'm going to get an F-test with 5 numerator degrees of freedom. Likewise, here is the F-test for the two dementia slopes. Here is the F-test for the biological or demographic variables, whatever I called them before. Here are the dementia group differences that I'm getting effect sizes for. And the other effect sizes I can get relatively quickly using pcore, which is a Stata command that spits out partial and semi-partial correlations and their squared versions. The only catch is that you cannot use the semi-partial versions for the dementia slopes because they have a common reference. So they're each individually not valid, but you can use it for all of the others. Then to get the change in the R-square that is attributable to dementia group, this is the extra work that Stata users have to do. They have to estimate a model that doesn't have the slopes they're interested in to see what the sums of squares for that reduced model is and throw it into the formula right here. So this is the extra part you do not have to do in your homework because it would be extra work for some programs and not for others. So this is what it is for dementia group because those are the two slopes that are omitted. This is what it is for age and gender because those are the two slopes that are omitted. So I have in the comments here what it ended up being. Okay, Stata users, questions on the code? So there's no effect sizes in this homework other than change in R-square. So you don't have to type all this. I just wanted you to have like a complete example of how I would do this. All right, R users. So I discovered something interesting about the Anova package that I had been using to help you get the residual variance up to this point. It also provides sums of squares that I had been ignoring. It provides the wrong ones. So that output is actually problematic. It provides, for each predictor, sums of squares that are known as type 1, which means that the predictor that's entered first gets credit for all of its prediction and any common. And then it adds the next one, and so it's like, and then order really, really matters. So that's no good. In almost every case, you do not want that. But I asked the internet about this problem, and the internet told me, oh, you need a different Anova package. And I shit you not, this one has a capital A, and it's written by a different person. And it provides type 3 sums of squares instead, and nowhere in the output would you know that. Seriously. So this might look redundant that I have lowercase Anova and uppercase Anova or title case. It is a different thing. So this is from a package called CAR. So if you wanted to make your own effect sizes for slopes that are directly in the model, you could get it out of the second set of Anova output. Otherwise, the new piece that our users need to know is right here. These are the examples of the custom F-tests. So here's the one for the overall model that has all 5 slopes listed in it. In this case, we put each slope in quotes, separated by a comma to denote numerator degrees of freedom, and we set it equal to 0. So it's kind of like a hodgepodge of Stata and SAS syntax. Here's the version that does just the dementia group differences. I'm then getting a semi-partial eta square. You don't have to do this part, but I wanted to show you how for the dementia group differences as the omitted terms. And then here's the one that lumps together age and gender as a separate hypothesis test and the corresponding sums of squares for that. And then last but not least, I'm getting effect sizes from the GLHT table that has the third estimate I was interested in for dementia, as well as for the stored model results. So you do not need to do any of that, our users. I just wanted you to have an example of what it would look like. Okay. Any questions on code for this? So again, trying to be crystal clear. New thing you need that you haven't done yet, right here. Writing out the slopes that you want tested simultaneously. So changes to the model. Did the slopes you added help? Lump them together, get your F to find out. So I have, I think, output in each program. Yes, I do. So the most comprehensive and easily provided output is from SAS. I get my test of the model. All 5 slopes work together to significantly predict cognition. How well do they do it? Explain variance, about 28%. Here are the type 3 sums of squares for each of the individual terms. And this is then used in computing semi-partial eta square for each term. So for instance, the semi-partial eta square for age is its type 3 sums of squares divided by the total, which is right here. It does it for you. So this one's okay, and this one's okay. These are the 2 that I can't use. The ones for dementia group, I cannot talk about semi-partial R-squares for them because they share a common reference category, and their total adds up to more than it should. So that's why I have do not report on those. What we do instead is lump those 2 together to get an F-test and a semi-partial eta square for their contribution to the R-square. So then that's what I have here. So it gives me the right sums of squares for the 2 that take into account their redundancy. It gives me an F-test, and here we go. Here's the F for it. The F for those 2 dementia slopes is right there, and their semi-partial eta square is right there. So of, basically, the model got 27% of the variance. About 18 of that is from dementia group alone. So semi-partial eta squares, again, the amount of the R-square that's due to that thing. The one I like. So in SAS, you get a contrast table that gives you your F-test for those things. In the other packages, in the interest of time, let me show you where those are. In Stata, the output will look like this. It will repeat the command that you asked it to do and clarify which slopes are being tested. In this case, it's all 5, and then it gives you an F-test and the probability of it. Now note that the denominator degrees of freedom for all of these tests are exactly the same. The only thing that changes is numerator degrees of freedom, which is the number of slopes being tested. So these F's are basically breaking the model into pieces. But the amount of slopes you could still add as denominator degrees of freedom is the same. And then here's all the effect size stuff. And what it looks like in R, here is the first Anova table. This is the one that you're used to seeing. And I had been ignoring it other than just this one number right here. So this is my residual variance. So this sums of squares for age is treating age as like special priority because it's first. Whereas this one down here, which is from the other Anova command, is treating it on equal footing as all of them. And the results are quite different. So everything looks like it's significant, but the size of the contribution is quite different. So recapping, ignore all of this. I only need this number. And I thought, well, maybe I can get that number from the other Anova. No, you can't. So the new Anova does not give you that number. So you still need both. By the way, residual variance is actually given in your model output for the coefficients. This little paragraph that's down here, residual standard error, that's your residual variance square rooted. So you could take that number and square it and get your residual variance if you wanted to. But I tend to avoid having people do things on their calculator because it gets to be repetitive. So I want you to have access to it directly on your output. Then the new part, the F-tests, it does the same sort of thing where it lists out what's exactly being tested, and then it gives you the F-test for that comparison. So that's the one for the model. This is the one for the 2 slopes for dementia group, followed by the corresponding effect size that I asked for, And then here's the one for age and sex combined and their effect size. Okay, those are the new things. We'll go through the solution next time since we're running out of time here. So I want to make sure that everybody knows what they're supposed to be doing for this week's homework. Do you feel like you can do this? Add a slope, tell me what happened. Add 2 more slopes, tell me what happened. Add 2 more slopes, tell me what happened. That's the story. And if you want to talk through the logic of any of your results section answers, I can do that. I can't tell you if you're correct, but what I can do is tell you whether the logic you're using is correct or not. Okay, so then we get all the R stuff, stata stuff. Yeah, that's data. There we go. And then at the end, I have a results section, but we're not there yet because we haven't talked about what the parameters mean. Why don't we do that real quick? We'll get it done. My intercept is 29. Who's that for? Yes, it's for the model, but what kind of person? So remember, the intercept is the you are here sign of the model. 29 is the expected cognition for what kind of person given the rest of the predictors. '85 is 1. So conditional on age, who can squeeze 9 pounds, who's a dude without dementia. That person has a 29. What happens to your cognition if you're older than 85? Yeah, it goes down. It goes down by 0.4 per year of age. What happens to your cognition if you're stronger than 9 pounds? Increases 0.6 per pound. So again, not wanting to use the word unit, right? We want to put the units in, help your reader out. So it's per year of age, per pound of grip strength. Who's higher, men or women? We got 1 vote for women, 2 votes for women. Got another vote for men. This is a minus sign right here. Men are the reference, women are the 1. Men are higher. Because the slope tells you how the 1 group differs from the 0 group. That means the 1 group's value is going to be brought down by the negative slope. Men are higher. And likewise, relative to the none group, the future group is lower by 5, the current group is lower by 16, and the missing comparison of future versus current is the difference of these 2 numbers right here, which is our minus 10. And everything's significant. Yep. So the direction is why I keep saying it's how the 1 group differs from the 0 group and how I keep having you practice that in your homework. Because knowing that the groups are different is not enough. We got to know who is doing better. Which direction is the difference in? So we might refer to this as something like the gender gap as a construct, the extent to which men are doing better than women in this sample. So then words at the end. So I've got a table. So typically in these sorts of analyses, you would report Pearson correlations to the extent that you can, as well as summary univariate statistics. So I've done that in 1 table here. Summarize the separate analyses, then put them all together. And here's the table that I made to describe each of the differences. And I put this in Excel so that you can see how I made these things as well. And that's it. We finished it. Hooray. All right. Any questions? or things that I can help with, clarify. Then that means on Thursday, we get to start a new unit. It's the moderation unit. It's one of my favorites. Moderation hypotheses are the idea that the effect of a predictor depends on who you are. Like, does the gender difference differ as a function of age? Does the gender difference differ as a function of strength? Is dementia equally bad for men and women? Those kinds of questions are moderation questions answered via interaction terms. So that's where we're headed next. All right, shall we call it a day then? We shall. All right, thanks for being here. See you next time. Let me know if you need anything. Peace out.